The prototype arrived at the Colt Patent Firearms Manufacturing Company facility in February 1917, crated and wrapped in oiled canvas. John Moses Browning stood in the testing room as the wooden panels came away, revealing the assembled rifle. Barrel forward, stock intact, gas tube visible beneath the fore end. 21 pounds of functional metalwork, each component machined to tolerances measured in thousandths of an inch. The weapon represented 18 months of design work, compressed into physical form. Browning had sketched the basic layout in his workshop in Ogden, Utah, working from the premise that automatic fire needed to become portable. The international struggle in Europe had demonstrated that sustained firepower could shape infantry engagements, but the heavy equipment delivering that firepower required teams of soldiers, tripods, and dedicated positions. The military requirement was clear: create something one soldier could carry and operate while moving. The gas system sat at the heart of the design. A port drilled through the barrel wall, positioned near the muzzle where gas pressure remained high enough to drive the mechanism reliably. A piston, extending rearward from that port, enclosed in a tube that ran beneath the barrel. A return spring providing the force to drive the action forward again after each cycle. The gas bled from the barrel would push the piston backward, and the piston would carry the bolt carrier with it, unlocking the breech and extracting the spent cartridge case. Browning lifted the rifle from its cradle, the weight distributed along its length, barrel assembly forward, action in the middle, stock and buffer system at the rear. He operated the charging handle manually, feeling the bolt carrier slide rearward on its rails, the extractor claw rotating into position, the magazine lips ready to guide the next cartridge into the chamber. The mechanical sequence played out in silence, each part moving through its designed path without the intensity of live activity. The barrel measured 24 inches, long enough to develop full velocity from the .30-06 cartridge, short enough to remain practical for a shoulder-fired weapon. The gas port location had required careful calculation. Too close to the chamber and the pressure would spike irregularly, potentially battering the mechanism. Too far toward the muzzle and insufficient gas would reach the piston, causing failures to cycle. The position Browning had chosen represented his best estimate of where that balance point lay. The magazine well accepted a 20-round detachable box. Not the belt feed of a heavy stationary weapon, but more capacity than a standard rifle's internal magazine. The box magazine design added complexity: followers, springs, feed lips that had to be precisely formed to guide cartridges reliably upward. But it allowed faster reloading than stripper clips and gave the weapon sustained fire capability without requiring continuous belt feeds. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. The United States had joined the overseas conflict in April 1917. By May, the Army Ordnance Department had contacted Browning with specifications for what they were calling an automatic rifle. Not a true rifle in the traditional sense, and not quite a machine gun, but something occupying the space between those categories. The requirement document specified shoulder-fired operation, sustained automatic fire capability, weight not to exceed 30 pounds, chambered for the standard .30-06 cartridge already in service. Browning had been 62 years old when he received that specification. He had already designed the M1911 sidearm, the M1917 heavy weapon, and numerous sporting firearms. His understanding of locked breech systems, gas operation, and recoil management came from decades of practical work, building prototypes, testing them, identifying failure points, and redesigning until the mechanisms functioned reliably. The challenge with the automatic rifle lay in simultaneous requirements that pushed against each other. Lightweight suggested simpler mechanisms and less material. Automatic fire capability required robust parts that could withstand repeated cycling stress. Reliability demanded margins in the design, tolerances loose enough to function when dirt entered the action, springs strong enough to maintain tension after thousands of cycles, gas port dimensions that would work across varying barrel conditions. He worked in a Hartford facility that Colt had made available for the project. The space contained lathes, milling machines, drill presses and measuring equipment precise enough to verify dimensions to a few 10,000ths of an inch. Browning would sketch modifications to the bolt carrier or gas piston assembly. Machinists would produce the parts, and he would assemble them into the working prototype to test how the changes affected cycling behavior. The pressure came not just from military requirements, but from production timelines. The Army wanted equipment in the field before the hostilities ended. Every week spent refining the design was a week that manufacturing couldn't begin. Browning balanced that urgency against his knowledge that deploying a flawed design would be worse than deploying nothing. A rifle that jammed in operation or broke under sustained use would undermine confidence in automatic weapons generally. The gas piston design he'd chosen was based on his earlier heavy weapon work, but scaled differently. The piston traveled with the bolt carrier through its full rearward stroke, a long stroke system that added weight but distributed the forces of operation across a longer time frame. This reduced peak stress on any single component. The bolt locked into the barrel extension through a rising lockpiece that cammed upward into locking recesses when the action closed. Unlocking occurred when the bolt carrier, driven rearward by the gas piston, cammed the lockpiece downward again. Each mechanism choice cascaded into others. The long-stroke piston required a stronger return spring to drive both piston and bolt carrier forward. The stronger spring required more gas pressure to overcome it. The higher gas pressure required a carefully sized gas port to avoid battering the action. The rising lock system required precise machining of the cam surfaces to ensure consistent timing. Everything connected to everything else in a web of mechanical relationships. The gas system operated on principles Browning had refined through previous designs. When a cartridge fired, the expanding propellant gases drove the projectile down the barrel. As the projectile passed the gas port, positioned approximately 4 inches from the muzzle, a portion of those gases bled through the port opening and into the gas cylinder that housed the piston. The gas pressure against the piston face created rearward force. Because the piston connected rigidly to the bolt carrier through an operating rod, that force translated directly into rearward motion of the entire bolt carrier assembly. The bolt carrier weighed approximately 1 pound, and the piston assembly added additional mass. Moving that combined mass rearward required overcoming the resistance of the return spring, which Browning had calibrated to provide enough tension to drive the action reliably forward while still allowing gas pressure to cycle the mechanism. The timing of this cycle was critical. The bolt couldn't unlock until pressure in the chamber had dropped to safe levels. If the bolt opened while pressure remained high, the cartridge case, still expanded against the chamber walls, would extract forcefully, potentially causing mechanical failures. Browning's design addressed this through the combination of gas port position and piston mass. The gas port location near the muzzle meant that by the time gas reached the piston, the projectile had already exited the barrel and chamber pressure had dropped significantly from its peak. The mass of the piston and bolt carrier assembly meant that even when gas pressure began driving the piston rearward, the mechanism's inertia created a delay before significant movement occurred. This delay, measured in milliseconds, allowed chamber pressure to drop further before the bolt unlocked. The unlocking mechanism itself operated through cam surfaces. As the bolt carrier moved rearward, an angled surface on the carrier contacted a corresponding surface on the lockpiece. The lockpiece sat in a vertical slot in the bolt body, with its upper surface engaging locking recesses in the barrel extension. When the bolt carrier cammed it downward, those upper surfaces withdrew from the locking recesses, freeing the bolt to move rearward with the carrier. Once unlocked, the bolt and carrier assembly traveled rearward together. The extractor, a small hooked piece of spring steel attached to the bolt face, gripped the rim of the spent cartridge case and pulled it from the chamber. An ejector pin, positioned to contact the case base as the bolt reached its rearward position, pushed the case clear of the action through an ejection port on the right side of the receiver. The return spring, compressed during rearward travel, then drove the bolt carrier assembly forward again. As the bolt face met the top cartridge in the magazine, the cartridge was stripped from the magazine lips and guided into the chamber. The bolt's forward momentum seated the cartridge fully. The final portion of forward travel raised the lock piece back into its locking recesses, and the action was ready to fire again. This entire sequence, extraction, ejection, feeding, chambering, locking, occurred in approximately 1/10 of a second when the device fired at its cyclic rate of around 500 to 650 rounds per minute, depending on ammunition and maintenance conditions. The speed of cycling depended on gas pressure, spring tension, and the mass of moving parts. Variables Browning had balanced through iterative testing. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The initial test firings revealed problems Browning had anticipated but needed to quantify. The gas port size, drilled to an initial diameter based on calculations from the 30-06 cartridge's pressure curve, produced cycling that was either too forceful or too weak, depending on ammunition lot variations. Different powder formulations created different pressure characteristics, and the gas system needed to function across that range. Browning stood at the test fixture, a heavy wooden frame that held the rifle securely while allowing controlled operation. He had instrumented the prototype with markers that would show how far the bolt carrier traveled during each cycle. Too much travel, and the action was battering itself, stressing parts beyond their design limits. Too little travel, and the bolt wouldn't fully cycle, causing failures to extract or feed. The solution required enlarging the gas port in small increments. Each enlargement increased the volume of gas bled into the cylinder, increasing the force on the piston. Browning would drill the port slightly larger, fire test strings of 20 rounds, measure bolt carrier travel, examine parts for signs of stress, and determine whether to enlarge further or whether the current size represented the optimal balance. The process took weeks. The gas port that eventually proved reliable measured larger than his initial calculations had suggested. The discrepancy came from real-world factors the calculations couldn't fully account for. Gas leakage around the piston, friction in the operating rod guides, variations in chamber pressure from different barrel temperatures. Theoretical models provided starting points, but functional reliability came from empirical testing. The buffer system also required adjustment. A spring and plunger assembly in the rear of the receiver absorbed the impact when the bolt carrier reached its rearward limit of travel. The buffer prevented the carrier from striking the rear of the receiver directly, which would have caused deformation and eventual failure of the receiver metal. The buffer spring rate needed to be strong enough to cushion the impact without bouncing the carrier forward prematurely. Browning tested different spring configurations, measuring impact forces and rebound characteristics. The final buffer design used a multi-part spring assembly that compressed progressively, softer initial compression giving way to firmer resistance as the spring compressed further. This progressive resistance smoothed the deceleration of the bolt carrier without creating harsh rebound forces. The trigger mechanism presented its own challenges. The rifle needed to fire automatically when the trigger was held back, but also needed a selector mechanism to allow single-shot operation. Browning designed a selector switch mounted on the left side of the receiver. In one position, the switch allowed the hammer to fall only once per trigger pull. In the other position, it held the trigger bar in position to release the hammer repeatedly as long as the trigger remained depressed. The timing between bolt lockup and hammer release required precise coordination. The hammer couldn't fall until the bolt had fully locked into the barrel extension. If the hammer fell while the bolt was still moving into position, the cartridge might fire before proper lockup occurred, potentially causing a critical mechanical failure. Browning used the bolt carrier's final forward movement to trip a sear that held the hammer until lockup was complete. The weapon entered service in September 1918, officially designated as the Browning Automatic Rifle Model of 1918. The military doctrine it was designed to serve, walking fire, the concept of soldiers advancing while firing automatic weapons from the shoulder, would prove problematic in practice. Operating a 21-pound rifle while walking produced accuracy that planners had overestimated. The physical demands of carrying the equipment plus ammunition loads exhausted personnel faster than anticipated. Yet the rifle itself functioned. The gas system cycled reliably across varying conditions. The locked breech handled the 30-106 cartridge's pressure without failures. The magazine feeding proved dependable enough for sustained use. The engineering had solved the problems it was designed to solve, even as the tactical doctrine proved less practical than hoped. What became clear over the weapon's service life, extending through the mid-century global conflicts and into the 1960s, was that the automatic rifle concept succeeded not because of walking fire, but because it filled a different role. Infantry units used it as a squad automatic weapon, operated from prone positions or rested supports, providing suppressive fire while other personnel maneuvered. The role Browning had designed it for transformed into the role it actually served. This transformation revealed something about engineering constraints and innovation. Browning had optimized the design around specific requirements: shoulder-fired operation, automatic fire capability, individual portability. Those requirements came from a tactical concept that would prove fleeting. But the engineering decisions made to meet those requirements, the gas system design, the weight distribution, the magazine capacity, proved durable enough to serve different tactical applications. The BAR remained in American service for nearly 50 years, not because the original doctrine was correct, but because the hardware was robust enough, reliable enough, and adaptable enough to fill roles its designer hadn't specifically envisioned. Later, automatic rifles would be lighter, would use different gas systems, would incorporate lessons learned from the BAR's service. But the fundamental engineering compromise Browning had achieved, portable automatic fire from a shoulder weapon, established a category of infantry equipment that would persist. The final curiosity lay in this gap between design intent and actual use. Browning had created a functional solution to a tactical problem that proved less significant than anticipated. Yet the solution outlasted the problem because the engineering itself was sound. The gas port he'd carefully sized, the bolt locking system he'd refined, the buffer assembly he'd tested. Those mechanical details worked independent of whether the weapon was operated while walking or while prone in defensive positions. The BAR M1918 remained in production with modifications through 1945. Total production exceeded 350,000 units across multiple manufacturers. The basic gas system Browning had designed in 1917 remained unchanged through all production variants. Later modifications added bipods, changed barrel profiles, and adjusted stock designs, but the core operating mechanism, gas port, piston, bolt carrier, rising lock, functioned exactly as Browning had configured it. The weapon's influence extended beyond its direct service life. When other nations developed squad automatic equipment in the 1920s and 1930s, many referenced the BAR's design approach: gas-operated action, detachable box magazine, selective fire capability, weight light enough for one person to carry. Various international designs solved similar problems using different mechanical details, but the basic concept of portable automatic fire that the BAR embodied shaped how planners approached infantry firepower. Browning himself didn't live to see the weapon's full service life. He passed away in 1926 while working on other designs. The bar continued in use for decades after, carried by individuals who never knew the name of its designer or understood the engineering logic that made it function. The gas port size, the spring tensions, the cam angles that governed bolt lockup, these details operated invisibly, their significance apparent only when they failed or when later designers had to replicate their function. What the BR demonstrated was that engineering solutions could outlive the tactical doctrines that generated them. Walking fire as a concept faded from training within a few years of the weapon's introduction. But the rifle itself, designed to enable that concept, proved valuable for entirely different tactical applications. The engineering wasn't successful because it perfectly matched its intended use case. It was successful because it was fundamentally sound enough to adapt to different use cases. The legacy wasn't the specific mechanism Browning chose, gas operation through a long-stroke piston, but rather the demonstration that automatic fire could be made portable without sacrificing reliability. Later designs would use short-stroke pistons, rotating bolts, different locking systems, but they all built on the foundation the BAR established, that the engineering problem of portable automatic fire could be solved with careful attention to gas system design, action timing, and mechanical robustness. The weapon represented engineering as a discipline of constraints of weight, of manufacturing capability, of material strength, of operating pressure. Within those constraints, Browning had found a solution that worked well enough to remain in service for half a century. Not because it was perfect, but because it was reliable. Not because it revolutionized large-scale conflicts, but because it solved a defined engineering problem with mechanical precision. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.